and welcome to the lecture series on design and analysis of algorithm. Today we are going to study another data structure that is called Fibonacci heaps. In this lecture we will see what are Fibonacci heaps, how you can insert a new node in a Fibonacci heap, then at the end we will see how you can merge two Fibonacci heaps. So basically a Fibonacci heap is a collection of trees with either min heap property or this max heap property. Now in the data structures you have already studied what is a min heap. In a min heap the parent is always smaller than the child. Okay, here the parent node is smaller than the child node, so this is following a min heap property. And if the parent node is greater than the child nodes, so this is following a max heap property, and this was your min heap. So basically a Fibonacci heap is a collection of either min heaps or max heaps, and they are basically unordered. They are unordered trees and they can have any shapes, and all trees can be of single nodes, means basically your heap could be like this also. This is 1, 2, 3, 4, then again here 5, 6, and other nodes are of same degree. The degree of a node is calculated by calculating the number of children. Here the degree of this node 1 is 0, the degree of node 2 is 0, the degree of node 3 is 2, and the degree of node 4 is 0. Now this is an example of a Fibonacci heap. As you can see, the degree of this node 21 is 0, the degree of this 11 is 2, the degree of this 3 is again 0, here it is 0, and here it is 3. Okay, this is the root list of this tree, and the minimum element in this root node is this 3. Okay, so your h min pointer will point to this node, and in this tree you can see that these circles, these red circles, they are indicating the marked nodes. So basically a Fibonacci heap is a collection of marked and unmarked nodes. These unmarked nodes are denoted by the value false, and they are denoted by the value true. So they are Boolean values. Okay, and the data structure which is used to store a Fibonacci heap is a doubly circular linked list. Okay, so this 21 will hold the value of this address of this 11, and 11 will hold the address of this 21. Again this 11 will hold the address of this 3, 3 will hold the address of 11, 3 will again hold the address of 8, 8 will hold the address of 3, again 8 will hold the address of 17, 17 will hold the address of 8, and then again this 17 will hold the address of this 21, and this 21 will hold the address of this 17. Similarly on the child level, this 12 will hold the address of 14, 14 will hold the address of 12, this 16 will hold the address of itself. Similarly here 12 will hold the address of 18, 18 will hold the address of 20, 18 will hold the address of 25, then 25 will hold the address of 18. Similarly this 25 will hold the address of 20, and this 20 will hold the address of 25, and this 26 will hold its own address. Okay, so the data structure which is used to store this Fibonacci heap is doubly circular linked list. Now let's see some of the terminologies related with a Fibonacci heap. So let us suppose that this is your heap H. Okay, and here you can see that this 7 is smaller than this 11, again 22 is greater than 13. Similarly these child nodes 8, 13, 18, they are greater than its parents. So basically it is following a min heap property. So this is a min Fibonacci heap. Now let's see what is min h. It is the minimum pointer, minimum pointing to the minimum of the root list. So this is your min h, the smallest value in the root node. Nh, number of nodes in the Fibonacci heap. So in this Fibonacci heap we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have total 9 nodes. Th, the number of root nodes in a Fibonacci heap. So here we have 1, 2, 3 and 4. So we have 4 root nodes. mh, the number of marked nodes. So 1, 2 and 3. We have 3 marked nodes. Phi of h. It calculates the potential of a heap. The formula is given as T of h plus 2 times m of h. So what is T of h here? 4 and m of h, that is 3. So the total potential of this heap is 10. Okay. So these are the terminologies related with your Fibonacci heap. Now let's see the first operation in a Fibonacci heap. Suppose we want to insert a node 25 to a Fibonacci heap. So let's follow the algorithm. First, what you will do, you will create a node x. Okay. So this will be your node x. You will write the value here. Okay. Now you will check whether the heap is empty or not. So in this case, the heap is empty. We do not have a heap now. So if the heap is empty, make x as the only root node in the root list. So this is your root list. This will be your root list because you do not have a heap. So this is your the only node, and you will point h min to this, and it will point nil as its children. So when the heap is empty, this is how you insert a node, or this is how you create your first node in a Fibonacci heap. Now let us suppose that we have a heap. Let's see how you insert a value in that given heap. Now let us suppose you want to insert 25 in this given heap. So you will create a node x, okay, and check whether the heap is empty or not. Since the heap is not empty, then you will go to the else part and you will insert the node in the root list. Okay, so this 25 will be inserted in this root list. This was your previous heap and h min was pointing at this position. So this node will be inserted to the left of this h minimum. So your new heap will become 7, 5, 25, 1, 11, 19, 8, 56 and this 8. Okay. Now you will compare whether this inserted value is less than this previous min. If it would have been less than this previous min, then your h min would have been updated. But since 25 is greater than this one, so your h min remains at this position only. So you can see that while inserting, you just have to manipulate some pointers because you already have the access to this h min, and you are just manipulating some pointers to get access to its left side. You are inserting a node at a given position in a linked list. So the complexity to insert is constant in a Fibonacci heap. Okay, and the complexity to find the h minimum, the minimum of the heap, is also order of 1 because it is always maintained by the pointer h min. Okay, now let's see the union operations. Suppose you have two heaps. This is h1, this is h2. This is the root list of your h1 heap, and this is your h1 min. This is the root list of your h2 heap, and this is your h2 min. So to concatenate these heaps, you just join the root list. Okay, you just join the root list of the Fibonacci heaps, and then you compare the values, which one is minimum. So here in this case h2 is minimum, so your final h min will become this. So this will become the new h minimum of the heap h. So here also you can see that you have to just extend this pointer. Okay, and there is one constant operation to compare. So while extending this pointer, it takes constant time, and while comparison, it also takes constant time. So union operations also take constant time in a Fibonacci heap. So in today's lecture, we have seen what is a Fibonacci heap. Okay, then we see the terminologies related to Fibonacci heap. Then we see how to create a node in a Fibonacci heap, how you can access the minimum of a Fibonacci heap, how you can insert a node in a Fibonacci heap, then how you can merge two Fibonacci heaps. So all these operations, create and access minimum, insertion and union, they take constant time. In the next lecture we will see how to decrease a value of a key, then how to extract min, and how to delete a node from a Fibonacci heap. Till then, thank you.